Okay, so hi, good afternoon, everyone. So welcome back to Plan 252, right? Transport modeling. Okay, good. So today's agenda is you have done your quiz, right? So and then you will present your project today. Okay, and then we will discuss about mainly what shortest path, yeah, dynamic programming, and then we continue with the traffic assignment that we have uh, have okay last meeting. Okay, so and then if we have time, so we can continue with traffic signal. Okay, okay. So it's your turn now to present your project. I think you have submitted your presentation last night, right? You can start. Who will present first? Uh, I think we have two groups, yeah, in the class. So go ahead. So we will present first. I will stop sharing some and put you into co-host so that you can present. Okay, go ahead. Who will present first?
Hi, Prof. We're the group two. I think we
Okay,
can present first. Sure.
good. Yeah, I can see.
Oops. Okay. Can you hear me?
Yes, yes, can see.
Okay. So good evening, group mates, classmates, Professor Cardi. So today we're going to just present our progress so far. This is still initial, but we've made some progress in defining the network. So our study is about the Cubao Intermodal Transport. Data was gathered in a field visit last November 11, last Tuesday, and Google Earth, and of course, we used resources of Revolut. So this is the network that was produced in the IFL lab. So some characteristics of Cubao, it's a trip attractor. So Araneta Coliseum has concerts, sports games. So there's events here, and then there's offices in this area. So there's offices here, and then there's retail experiences. These are malls here, and then there's a farmers here. This is basically a mall area, and then there's also some residential here in this part. Entertainment and niche retail. There's Cubao Expo here. So these are some trip attractors, and there's some trip generators in this area. Multimodal exchange. It hosts light rail transit, LRT2 station, metro rail transit station, bus station here, and utility vehicle express stations and jeepney station. It also functions as a node in a regional context. So it functions as an origin and a destination, intermediary transfer point that enables passengers to other destinations rather than terminating travel in Cubao. So our objective is to describe and model the network flow in Cubao during peak hours. This is because our time is also during peak hours we can gather the data that time. Recommend price policy that may improve network flow and decrease congestion during peak hours. Uh, so, th- so that's our objectives. So allow us to different stations here. So we have a bus terminal here. There's a bus stop along EDSA here. There's two train stations, the MRT and then the LRT. There's one jeepney terminal here, and then there's two UV Express terminals here. And these are the routes that are available for each no for each terminal or station. So there's 21 routes for the buses here. Oh, wait. No, sorry. There's 18 routes here for this bus terminal. There's three routes here for EDSA bus stop. And then there's two routes for MRT, northbound and southbound. And then there's eastbound and westbound for LRT2. And then for the UV station here, there is uh, two destinations, Novaliches and Marikina. And then here, there's San Mateo, Rizal, Antipolo, and Rodriguez here. Jeepney terminal here, there's five routes. So these are the routes that we've identified for the Cubao. As you can see, here are the train stations. This is LRT2 outside, and then this is the MRT. So the assumption is 1,405 people per train set. Uh, Yun. So, and then next for the UV Express, um, this is for this station here, Novaliches and Marikina, SSS Village, and this is also eastbound, here. So our SUV assumptions is 14 people per SUV, and then 1.6 PCU per SUV. So this 1.6 PCU, this was presented by in the last presentation of Prof. Cardi. For buses, there's two types of buses here. These are the EDSA buses, and then there's a smaller bus here in the transport terminal. So these are the three routes here for the EDSA bus, and these are the other routes here. So our assumptions is that we need to confirm is 30 people per bus with a PCU of 3 PCU per bus. And then here the jeep, there's these are the routes. There's eastbound and there's northbound for Project 4. And then here, eastbound Silangan, Cainta, and Antipolo. And then for the jeep, there's 22 people per jeep. There's 10 per side, and then there's two in front, and then 2.2 PCU per jeep. So this is the transport terminal. And there's a depot, small depot there for the jeeps. We're not including in our study the taxis and then also the tricycles. So it was only observed that the tricycle is here. It's not inside our study area. Plus, it's only the last mile that they use this for. So for the taxis, I think it'll be hard to gather data for this one. Our next steps is we're going to gather survey. We're gonna survey some people. These are some questions. We already have our tool. So these are we'll be asking trip purpose, trip origin, destination, cost, PHP per trip, time cost, perceived comfort, perceived convenience, and socioeconomic, age, gender, occupation, and salary. And then, of course, the consent. The transport nodes that we'll be gathering are here. For the EDSA bus stop, it might be hard to gather data because it's along the main highway, so I don't think it's feasible to gather data there. So we'll just focus on these ones. So our initial sample size is 20 respondents per node, so times 6 or terminals. So that's 120 respondents. So maybe 15 to 20 respondents. So that's 90 to 120 respondents. We'll see how much data we can get. Um, that's it for our updates.
Okay, good. Is there any input from other groups to this group? So I guess you are going to make from this survey you're going to make uh, so trip chain, trip distribution, and then modal split, isn't it?
Yes, sir.
Yes. And then from there you will get people trips, and then per node, yeah, and then from where to where, yeah, those are the nodes, right? And then you need to convert this to BCU. Is that correct?
Correct, sir.
Yes. Okay. So then you can load this into IFN transport. Okay. At this point, the IFN transport has no layers, so only one layer. So in that case, you only have one type of vehicles rather than multi layers. Okay. But anyway, you already converted everything to BCU. That
PCU.
means yes, everything is fine. Okay. One thing only. You assume there is capacity, okay, but in reality there is also load factor. Yeah. So not all public transport are full into capacities, and
Hmm.
so probably you need to check the load factor. Okay. So maybe 80% or maybe 50% full. I don't know. So that kind of things you need to include, yeah, in reality. So. Uh, With that, you can input. So to input into, yes, John Kenneth, you want to ask something?
Regarding what you said, sir, about the load factor, do we just assume the average per day?
Yes, you can assume or based on the sample, you can check, okay, uh, what is it full capacity or actually only 80% and so on.
Copy, sir. Thank you.
Okay. So if you use IFN only, so there is no OD, right? Because IFN itself is a strongly connected network, but you can still include what is called cloud node, yeah, meaning external environment. And then from the cloud node, you connect to the node of origin and the node of destination. So of course, from the cloud node to the node origin, and then from the destination, go back to the cloud node. Okay, so the cloud node is just a tool, modeling tool. Okay, there is no real things there, but you add there so that you can model external cloud, meaning external environment outside of the study area. And those, so from where to where, okay, so the OD is still there if you want, because you have certain production and attraction there, right? So you can still include if you want. Okay, I think
And
that,
I have a question, Prof.
yes, please.
Since we have a lot of routes, can we cluster them into areas?
Yes, if you want to cluster, uh, what the meaning of clustering into area? You want to create zones?
Yes, Prof. Like Rizal, QC.
Oh,
There's
yeah,
one. Yeah.
that's what we do. Okay, so uh, based on the geographical area, so where are they going? To the north or to the south? Of course, there will be different, right? So this is something outside of your study area, isn't it?
Yes, Prof.
Yes. So that will be some kind of destination node that you put, right? So in the south, they will go say the name. What is that? The name of that. So each of this area, okay, outside of this, you can create a zone or cluster, and then there is some kind of centroid node, okay, in the south, east, west, and so on. Okay, and you can include that. Okay. Uh, if you go to the example in and transport. Okay, there is a example of Ateneo, the Manila at the time. So it was started in 2011. So the map is only along Katipunan, isn't it? But if you notice, okay, there are other nodes that is actually offset. So Marikina, UP, Eastwood, and so on. They are actually part of this. So they are different zone with this inside. Okay, so that did I answer your question? Similar, right? Okay. Okay, good. So you have almost about 1 month or maybe less than 1 month to finish. Okay. And if you have any problems, so you can discuss separately outside the class if you like. Just set a point. Yeah. Good, thank you. Is there any comment or input to this group from other group? Okay, so if not, so yeah, thank you. So go ahead, the next group. Yeah.
Okay, sir. I will be presenting on behalf of group number 1, the Katipunan group.
Okay.
Uh, can you see the presentation po?
Okay. I can see
Yeah.
now.
So basically, this is our progress for the Katipunan group. So basically, for the objectives of the study, we retained the uh, assessment of traffic flow, speed, and congestion for Katipunan Avenue. And then to assess the impact of introduction of flyover, U-turn slots, and open intersections. This will be our alternative scenarios. And then lastly, to provide science-based and data-driven information for traffic improvement in the area. So this is our research questions. Basically, these were also retained from our previous presentation. So, but I'll proceed directly to the progress that was made by the group. So again, we'll be using the IFN tool that was developed by our professor. So again, our base scenario is the existing situation in Katipunan where you have U-turn slots or under Katipunan flyover near Miriam College and CP Garcia Avenue intersections and signalized intersections in front of Ateneo Gate 3, Miriam College, and CP Garcia Avenue, and a close intersection in La Vista. So for the alternate scenarios, we have identified 5, basically 3 involving the construction of flyover from UP Town Center to in front of Ateneo or in front of Miriam. And then the first alternate scenario, U-turn slots are still in place, the intersections are open for the first scenario. For the second scenario, U-turns are still in place, intersections are closed. And then the third scenario, U-turn slots are not in place and the intersections are open. And then the fourth and fifth scenario uh, just will cover scenarios wherein the flyover will not be constructed, and then the U-turn slots are in place for scenario 4, and then intersections are open. And then the fifth scenario are U-turn slots are not in place, and then the intersections are open. So again, the flyover scenario, there are 2 proposals that were forwarded by DPWH, one involving a shorter flyover from UP Town Center to in front of Miriam College, and then another scenario, a longer flyover from UP Town Center to in front of Ateneo. So we have already had an initial base scenario computation that was that we did a few weeks ago, but we have encountered some problems. But because in order to run the alternate scenarios, we have, upon inspection of the base scenario, we have identified that there are certain road links that were absent, specifically Saberville Avenue, Langka Street, Maginhawa. And then the U-turn slots were not actually captured by the OSM downloader in the tool. So maybe prop as uh, an addition as a point of improvement for the tool, we suggest that you include links because uh, we have identified that the U-turns and certain roads are captured either by primary link, tertiary link, or secondary link. And the online tool doesn't capture that. That's why we have only captured this for the base scenario computation. But what we did upon learning this is to use ArcGIS. Later, I will discuss how we did a workaround for this problem. And then also, yeah, I also explained earlier that again, we cannot compute using the uh, the alternate scenarios can't be tested by the uh, base scenario that was used earlier. So what we did is, again, downloaded the OSM datasets from OpenStreetMap. And then process it using ArcGIS. So basically, we also have expanded the study area because the proposed flyover, actually, the goal of that flyover is to um, improve traffic flow in Katipunan, specifically catering for vehicles coming from the northern area, specifically here in Commonwealth Avenue in the north and Congressional Avenue and Luzon Avenue in the north. So we have expanded upward north the study area and then on the south as well. So basically also capturing some up to EDSA and some parts of Marikina and up to the north to the Nangsora area. So we have cleaned this using ArcGIS and then we have reassigned link capacity. So we have seen as well that uh, the OSM datasets does not include the correct number of lanes. So we have put into the ArcGIS the correct number of lanes for each link scenario. And then the creation of new node matrices. This was also done as well. So, and then currently, right now, we are in the process of creating new link matrices for both the base scenario and the alternate scenarios. Again, using OSM datasets. So for our next steps, we would rerun the base scenario using the expanded study area and the new node and link matrices, and then running of alternate scenarios later on. So again, that's it for our team that's composed of my group mates, me, Ms. Dian, Sir Dennis Buena, and Aaron Francisco. Thank you po.
Yeah, thank you. Thank you for the good input. Did you actually use the all road type?
Yes, sir.
Okay.
Unfortunately,
If
it
you don't
Google
clean, if you don't clean up, maybe you because you check the to largest strongly connected. If you don't clean up,
yes, sir. Um, we tried. Actually, we tried um using a number of combinations. Check and uncheck road types and check and uncheck clean to largest strongly connected components before uh seeing it. And then again, I we have seen some problems in terms of again the U-turns and certain road links are not captured specific, because if we want to capture the U-turns, basically we have to provide additional options for checking the primary link, secondary link, and tertiary links. And then for the cleaning of largest strongly connected components, honestly, sir, to what we did is just since we are working in ArcGIS, we just make sure that there are no hanging nodes. So hopefully, when we put it in the online system later on, this will run smoothly.
Okay, very good. So, probably there are some type that I miss there, right?
Yes, yes, sir. You had
If you know
specifically.
to please send by the chat or so that I will know what type of things that miss I can add that. Yeah.
Okay, sir. I will make an email and I'll
Yeah.
send it later.
Thank you. Thank you. And then for alternative scenario, of course, IFN transport cannot be used. So surely you need ArcGIS to or QGIS to solve
Yes,
that.
sir.
Right? Okay, good. And I have very old data, so 2011 data along that side. I think I put it there as example in Transport Ateneo. That is the real data from the survey 2011. So in that case, you need to project up to
Okay,
this
sir.
year. And if you need the report that I've done in 2011, I have it. So you can just DM me and then I can send it to you.
Okay, sir. Much appreciated po.
That include all the recommendation and data at that time. Yes. Okay, good. And there are several proposal on that flyover. Which one do you use actually?
Again, we'll be using the scenario, a shorter flyover from in front of UP Town Center, that's behind UP, to in front of Miriam College.
Actually,
And then the
so
other longer flyover that DPWH proposed was from UP Town Center up to in front of Ateneo.
so that is not including. There is also another proposal from the LRT up to Miriam. Is that not included?
Uh, no, sir. We
Okay.
didn't include that proposal, the inclusion of LRT from a, I think it was um, um, a different line that would connect LRT 2 and MRT 7.
Okay. You just DM me. I can send you the
Okay, sir.
proposal also. Okay. No
Okay,
problem.
sir.
Yes. That is very good. Thank you. Yeah. Is there any comment to this group from the other group or question probably? Okay, so if not, I would like to remind you about uh, what is that? The evaluation for the faculty for this class. So please input your evaluation for the class for improvement of next semester. Okay. Okay, so let's start our lecture. We go to shortest path. You can go to Moodle. There's an updated version of shortest path there. Can you see my screen? Okay, so today we will mainly learn about shortest path and dynamic programming. Okay. Okay, so shortest path is one of the uh, significantly important algorithm, okay, for transportation, especially. Uh, this has been the work of many people. Yeah. So why this is matter? Because if you know the shortest path, so you can minimize the travel time, right? For fuel consumption, for example. The same thing, you can reduce congestion by inputting into uh, traffic assignment model, similar to that we discussed last meeting. Okay. Uh, and you can enhance the route planning, okay, for logistics, for public transport, and so on. So, of course, the algorithm itself has been used for many different applications. Okay, so one of them is Google Map, and Waze, isn't it? So if you know the core component of this algorithm, then you can actually think of something new that you can use on your own. Yeah. So including your own probably delivery or freight delivery or emergency response. Yeah. In pedestrian and cyclist path finding, we can also create that. Yeah. There is also a software called OpenTrip Planner. Can you search? It still exists or not? OpenTrip Planner. Oh, there. This one. Can you see my screen? OpenTrip Planner. Okay, so this is also very useful. This is open source and free. Okay, and I think several companies, including in the Philippines, they are using this also to create uh, project, yeah, for public transport, for example. So you can, the code is free, so you can also use this if you want. There and GitHub. Yeah. Okay. Now come back. So inside that OpenTrip Planner also have sorters algorithm inside. Okay. So then for our purpose in this class, why we study this, because this is the core component, the core algorithm for traffic assignment, isn't it? Remember last week we talked about all or nothing, yeah, and then from all or nothing, okay, the core component is actually calculating the shortest path, right? And at that time, I said, okay, let's forget about this for a while. Okay, next time we will discuss more detail. That next time is today. Okay, so the idea is you have two nodes, okay, origin and destination, and then you need to find the most efficient route. Okay. So now you have a network, of course, that's the input data with certain link costs. Yeah. The cost can be distance, can be time, can be any cost. Remember, when we talk about cost in transportation, we talk about generalized cost, which include the cost, time, uh, uncomfort, and so on. Yeah, so many factors you can input into generalized cost. Similar to what uh, group 2 a while ago putting into the survey form, isn't it? So now, given the source node, yeah, or the origin, yeah, and the sink node, which is the destination, and the origin represent the supply, and destination represent the demand. Okay, now you want to find the path. Path means you get the sequence of node or a sequence of link, okay, that would minimize the total cost. Yeah. So there are many algorithms. Okay, the most well known is Dijkstra, which is an A star. A star is used for game. Okay, Dijkstra, I think they use it for OpenTripler and many others. Okay, Uh, but if I discuss this, it will go too much detail to the data structure and algorithm of the computer science. So this is not for you. Okay, so today we'll just only discuss these two, yeah, dynamic programming and linear programming. So this is for you. Okay. Why? Because once you understand the tool, okay, you can use it not only for shorter path, okay, but you can use it for many other things for your life. Okay, so let's go to the first part, yeah, with this dynamic programming. Yeah. The most important part here is you need to understand the principle, yeah, what is called a principle of optimality. Because when you understand this, you can use this for any other cases, not just shortest path. Okay. Okay. So what is DP or dynamic programming? Yeah. DP is actually a mathematical method, okay, to improve the computational efficiency by decomposing the problem into smaller and simpler sub-problems. So this is the main part of this. So if you have a problem, you need to divide and conquer, isn't it? Okay. So this is exactly dynamic programming. Okay. So the purpose is to sort what is the optimal policy. So when we say policy, it's just the sequence of nodes. This is a path. Okay. So you can use this for any application, not just for shortest path, but the idea of shortest path is easy to understand. Okay. So you search for optimal policy for sequential iterative decision-making process. So this is actually for decision-making originally, yeah, not only for shortest path. Now, how to use? So you transform your problem, any problem, in fact, including business problem, your life problem, okay? You transform your problem by finding the optimal policy, including n component, okay? And to sequential decision process of n separate stages. So I understand these are big word, okay? In the moment you will understand what's the meaning of this one. Yeah. So basically what you will do is you find the sequence of node or sequence of link. Yeah. Okay. And then the way you do is to make this sequential decision in n separate stages. So you have what is called recursive fashion. Okay. So the basis is called principle of optimality. Okay. So there are many terminology that you should understand first, otherwise you will get confused. Okay, so I will just use a network. So in this case, directed graph. Okay, and when we say state, okay, state is basically a node. Okay, where you make a decision. Okay, and then when you make decision, that means you are selecting the outlink. Okay, you're selecting the outlink from the node. That's the meaning of decision here. Okay, and when we say decision policy, okay, you're practically creating the path, the route. Okay, from initial node to the goal node. Yeah? So from origin to destination. So you will get sequence of node or sequence of link. Yeah. So if you are not understand directed graph, so you can go to my website. This link. Last time we discussed about this, so I believe you already got the meaning of graph. Yeah, graph is basically node and links. Okay. So what is the principle of optimality? So DP or dynamic programming is developed by Richard Bellman in 1957. Okay. He said that optimal policy has property that whatever initial state and initial decision are, the remaining decision must constitute an optimal policy with respect to the state resulting from the first decision. Do you understand the meaning of this word? Okay, so the point is, if we know, okay, how to proceed from intermediate state to the final state, then we should follow this regardless how to get from intermediate state, or how to get from initial state to that intermediate state. Do you understand the meaning? So if you have, okay, let me give you example here. So this is a network, okay? So this is your initial state, right? So this is your initial state, and this is your goal state, okay? So, Berman principle of optimality said, okay, I have any node, let's call this node intermediate state. And I know from intermediate state to the goal state is already optimal. Okay, assume that you know from intermediate to the goal state is optimal. Okay, that means, okay, I just continued in this fashion. Okay, if I want to get from initial to the intermediate, okay, I will just need to find the optimal from initial to the intermediate. I don't need to care from intermediate to the goal state anymore. Do you get the idea or not? The meaning is now you can separate the problem into two parts. The one that you have solved and the one that you did not solve yet. Okay? This is how you do divide and conquer. Let me put back again the previous slide so that you can see clear. Okay. So again, okay, if we know how to proceed from intermediate state to the final state, that means you already know, right? Okay, then we should follow this action, so you don't need to care anymore because you already know. Okay, regardless how to get from initial state to intermediate state. So you divide the problem. One is already solved, the other one is not yet solved. Okay, so if you do it this again and again, recursively, you solve all the problem. Okay. Okay, yeah. So if you know from intermediate to the goal state, okay, then all you need to do is to think how to get from initial to the intermediate. Like that. Yeah, so here, if we know the best path from intermediate to the desired state, the goal, regardless how we get from initial state to this intermediate, yeah, we should proceed along this path. Yeah, I, J, K, L, N. So this one, the one that you already discover, you don't need to think anymore because that's it. You already discover like that. Okay. Okay. Yeah. So if you know this, okay, this is the one that you need to think. Okay. That what is the implication of very simple principle? Yeah? Of principle of optimality. That means if you have any complex problem, okay, you can break down your problem into simpler sub-problems. Okay, then you find the optimal substructure rather than the whole structure. You just find the optimal substructure. Yeah. So if you can find that, okay, that is equal to the solution of the entire problems. So you divide your problem into smaller parts. Okay. Okay. Now, then you need to do, in a way, what is called recursion. What is the meaning of recursion? Okay. Recursive function, okay, basically represent a nested function. It's a function that calls itself. Yeah. So To do recursive function, you need to have two things. Yeah, one, you need to have boundary condition. Okay, and then the second one is you need to know how to exit from that function. Okay, so this is actually one of the most important mathematics. Yeah. So this is called difference equation or dynamical systems. Okay. So I have the tutorial in Reveledo. You can check more detail. Usually I keep this one semester just for this alone. Yeah. Very deep. Yeah. Because it will include stability, solution, and so on. Yeah. Anyway, let's go to the simplest one. Yeah. This is called Fibonacci. No, this is the recursion of factorial. Okay. Can you see the, okay, how I will know it's recurse? You will see this notation and the subscript. Yeah. There is a n here, and there is n minus 1. Right? So the next point n depends on the previous point. So any function that it's called itself is just different time, that is a recursive function. Yeah. So let's say this is, it will produce factorial. So look at this. First we put boundary. Right? So say f1 is 1. So this is given. Okay. What will happen if you have f1 is 1? So in this case, now you want to get f2, right? So if you want to get f2, what you will do? N is 2, right? So in that case, you put n is 2 and then multiply by n, f, n minus 1. What is this? This one. N is 2 minus 1 is 1, so it become f1, isn't it? So, but f1 is already given, no, 1. So in that case, you have 2 times 1 equal 2. Is it clear or not? Yeah. The same thing if you have f3, if you want to find f3, yeah, so you use this formula, okay, n is 3, that means this one become f2, because 3 minus 1 is 2, isn't it? So then you will have 3 times f2, but f2 already computed, so you have this one. Okay, so 6 and so on. So this sequence, okay, is basically factorial, isn't it? So you can get factorial using a recursive function. Okay, this is just an example of recursive function. Okay, I give you another example. Our grade, yeah, in this class, okay, for the project, for the assignment, for the quizzes, is based on Fibonacci, right? Okay, so yeah, this one, if you want to do factorial a while ago in Excel, yeah, you can just put this 1, and then this one is n is plus 1, right? And then initially you have 1, and then what is the formula a while ago? This one multiply, yeah? So in that case, you just multiply, yeah? So V2, this is the previous value, multiply by n, yeah, this is the n. So you will get that factorial. So now this is Fibonacci. Okay. So Fibonacci is second order. That means you have two initial value. Okay. So say initial value is 0 and 1. Okay. For Fibonacci, then this is given. Yeah. Boundary value is given. Yeah. If the value is not 0 and 1, you will not name it Fibonacci. It become a Lucas number. Yeah. Anyway, so let's start with this one so that you will understand. Remember how I will know this is actually recursive. You will see the subscript here, and then this is previous one, and then this is two previous. Yeah, like n is today, n minus 1 is yesterday, n minus 2 is 2 days ago. Is that clear? Yeah. If n is this month, okay, then n minus 1 is last month. And then n minus 2 is 2 months ago, like that. So, and the time depends on you to decide. Yeah? Is it today or last minute or last month or last year? That depends on you. Okay? So, now if you input this formula, okay, so because I already know F0 and F1, okay, I want to get F2, right? So that means F2, n is 2 now, equal to n minus 1, so that means 1, and then n minus 2. So 2 minus 2 is 0, isn't it? Okay, so but F1 is already given 1, and then F0 is already given 0. So I get F2 equal 1. Okay, so next again, F3. What is the meaning of F3? F3, n is 3. Yeah, so, and then n minus 1 is 3 minus 1 become 2 there, 2. And then n minus 2, 3 minus 2 become 1. Oh, but F2 is already computed, equal 1, isn't it? Okay, and then F1 is already given here. So you just input back, so you will get F3. Is it clear or not? Yeah, so if you continue with this fashion, you will get this kind of sequence. So this is Fibonacci sequence. Okay, so any question about recursive function? Clear? Just function that call itself. Yeah? Okay. Now, yeah, this one maybe no need, yeah, for you. Okay, so this is another example of recursive function, yeah, that we often use, yeah, for money. Usually, we use this for money. So, formula, okay, is given here. Okay, the time is k plus 1, and then depends on the previous time. So the money for tomorrow depends on the growth factor A. It depends on the money today. The same thing, this one can be growth, not just money, it can be population growth. Yeah. And B, yeah, in money, B represent your payment for the loan, or the one that every month you need to pay, or the one every month you need to get for a pension. Okay, so and of course you need to put initial value because this is only order 1. Yeah? So you see the largest minus the smallest, that's the order. Yeah? The largest subscript and the smallest subscript, that's represent the order. Yeah. So that order represent how many boundary value you need to provide. Okay. So in that case, you can create a recurrent, yeah, function. It is the recursive function. Okay. So say you have y1 equal to a times y0 plus b, right? The same thing, y2, okay, equal to y1 plus b. Okay, and that one y1 already know, so you input that, so yeah, become quadratic, and then when you to get y3, you will get cubic equation and so on. Okay, so if you simplify, okay, this is actually a geometric series. Okay, so if you know, and this is geometric series, there is a closed form formula. Yeah, in high school you learn this, I think. Okay, so that based on that closed form formula, so you can simplify. Yeah, so if you have this closed form of this affine recurrent regulation like this, so then you can find this is the closed form formula from geometric series. Okay, then the answer will be like this. Yeah, this is the solution. So if you have that recurrent formula, okay, you will get a closed form formula, this one. And this is actually the one that you use in computing the growth and so on. Okay, anyway, so if this is too complex for you, just forget it, no problem. Okay, but let's come back to this is just to tell you about the recursive formula. Okay, let's come back to dynamic programming. So when you have a data table, okay, usually in data table you have row as your record, and then your columns, you usually the variables, yeah, the field. Okay, this represent dimension, right? So now when your data table, okay, have a lot of variables, yeah, a lot of dimension. Okay, now each variable have its own set of values, right? So then if you want to search, okay, the combination of search become what is called combinatorial explosion. It become exponential. Okay, so say if you have binary, only two choices in each variable, and you have n variables, then you will have two exponent to the n. Okay, so to compute this is too long. Yeah, so I usually, if you know how to program, you can try on your own. Okay, if you use Python, for example, you type like this. Yeah, this one is a problem because it will become exponential time. And if you try to get, for example, Fibonacci 100, it will not happen. Yeah, it will take very long time. Yeah. So in that case, if you use dynamic programming, okay, so you calculate using a previous value first, and then you memorize this. Okay, using this, suddenly everything become very fast. Okay, this is the point of why we use dynamic programming. Okay, just to compute very simple program of Fibonacci. Yeah, Fibonacci 1, 2, 3, 5, no problem. But when you start to make it Fibonacci 72, Fibonacci 100, then it start to become a problem because it become very, depending on how you code, become very long to compute. Yeah. Okay. So what is the general step in dynamic programming? Yeah. So first you need to define what is your objective. Okay, so what is your optimal value function? This is what is called objective function, yeah. And then you write that equations, yeah, something like this, yeah. So this is the one that you need to create. And that recursive function is the one that you create, yeah. So once you create that, okay, so you write the recurrent relation. Once you create that, then you note for boundary condition, then you solve it. And so don't worry, let's start with a simple example so that you will understand. Okay, I have a simple network, just one way road. Yeah, this is called a cyclic network because there is no cycle. Okay, so the numbers here represent the cost. Okay, so A to C is 1, yeah. C to E is 5. So these are represent the cost. Okay, so you want to minimize the cost, yeah, shortest cost, right? So you want to find the shortest path from A to B. Okay, so given this network, so what to do, isn't it? Okay, so what to do? So let's do it. This first you define what is called stages. Yeah, states. State with T, state, that means the node. States is a portion of problem that contain a set of mutually exclusive alternative, yeah, from the best alternative to be selected. That means now you start to create the stage, multi-stages. So here it is. How many stages do we have in this problem? Yeah. So the stage you can put vertical line, something like this. Okay. Can you distinguish state? Yeah, state with the, that means node, and states, yeah, with G. Yeah. The red line here is the states. Clear? So what you will do is divide these stages, yeah, states with G. Okay, this one. So you create that red line here. So one, two, three, four, five, six. So you have six only, yeah, six stages. The nodes are many, yeah, only 20 nodes here. So clear, yeah? Now, first, yes, Justin, you want to ask?
Sir, is it only because of the problem, but are the divisions always vertical?
No, not always vertical. So this is just because of this problem.
Okay.
Okay. This is simplified. So not always vertical. Okay, it can be curvy if you have. Okay. Let's check. Okay. Our goal, remember, you need to get the objective function, right? The goal is to minimize the cost. Okay. From any node to destination node, which is node P. Yeah. Can you see? So from any node K, K is the node, any, to node P. Right. So this is the, remember the three things I want to discuss with you. Define the optimal value function. That's the first thing, yeah. And then derive the recurrent relation and then boundary condition. So we are in the first part, yeah. So optimal value function is actually the S, this one, the SK. Yeah, this is the function. Okay. You want to minimize the cost, yeah, from any node to your goal node. That's the function, optimal value function. Now, example, yeah, I can replace this subscript K with C. Okay, C here, right? Right. So, can you see my mouse? Yes, okay, C is here. Okay, so from C to B. So that means minimum cost from node C to node B. Yeah. So if I put subscript SD, that means a minimum cost, D is here to B. So this is the minimum cost from node D to node B. Okay. I don't know that function. I just define the name. Is that okay? Okay. So now we are in node A, right? This is the origin, right? We are going to node B, that's the destination. Okay? So there are only two choices, isn't it? Either to go to node C or to node D. We don't know. Okay? So we don't know whether we go to C or D, and we don't even know the value of SC or SD. It's okay. We just keep name. Okay? But we know the cost of A to C is 1, correct? This is given. Yeah? And then the cost from A to D is 0, given. Yeah, this one. Okay, no problem. In that case, when you are in A, yeah, so what you will do, you define the optimal value function of SA. What is the meaning of SA here? I will go from, this is the minimum cost from node A to node B, the destination, yeah? Remember, A is the origin, B is the destination. Is it clear or not? And then in node A, what you will do, you will minimize the cost. How do you know the cost? The cost depends on this one to go to C with this one, right? And then SC. And then the other one is, the other possibility is to go to node B, D, with is 0, the link, no? And then ST. SC and ST, I don't know, no problem. I just put it, the name. Okay? So at this point, I get the function. Up to here, is it clear or not? Okay, so we define as A. So what you will do, we go to the next stage, right? We go to the next stage, what you will do. The next stage is, okay, so based on the principle of optimality, okay, you know that the best path from A to B, this one as A, right, has property that whatever initial decision at A, okay, the remaining path to B, starting from the next point, which is C or D, okay, must be the best path. Okay, so we already, the principle of optimality guarantee this is correct. You remember, yeah? I only know from A to C, this is what we get, okay? I tell to you that SC, which is from C to B, is already optimal, assuming, yeah? If I know the SC, this is optimal, then the whole thing SA is must be optimal, correct? Yeah? This is the guarantee only. Okay? Without that guarantee, this equation is wrong. Yeah, so that's why the principle of optimality is very important here. Okay, so now we don't know SC and ST, isn't it? Okay, no problem. So we go to the stage 2. Now we are in C and D. Okay, so if you are in C, what you will do? There are two possibilities in C, right? What is the possibility? To go to E or to go to F. What is that? Yeah. If you go to E, the cost is 5. If you go to F, the cost is 4. So this is the one that you input here. Right? So this is the cost, the link cost. And then principal optimality said, okay, that 5 plus SE. What is the meaning of SE again? That is the minimum cost from E to B. What is the SF here? That's the minimum cost from F to B. Okay? So this principle of optimality guarantee that this is minimum. The same thing with D, isn't it? So from D, where is D? Here. What is the possibility? Either to go to F or to go to G. Right. Okay. So if you go to F, what is the cost? 7. There. You have 7 plus SF. Yeah. If you want to go to G, what you will do? What is the cost? 3, isn't it? Here. Okay. Then you go 3 plus SG. Is it clear or not? So can you do it or not? Manually. Is there any question? Justin, every time you ask question, you need to claim. I did not see your claiming in your recitation. Sayang.
Sir.
Oh. Okay, so is it clear? You can SC. Yes, Joshua.
Yes, Prof. The cost for the previous, the one from A to C, is disregarded in the second stage.
No, it's not like disregarded. I'm just collecting all the equation here.
Okay.
Okay. I already know SA equal to depend on SC and SD. I collect this one. Okay. And then I go to the next stage 2, right? So I collect SC and SD. Correct? So I collecting all the equation. That's how you dynamic programming way is to collect all the equation that you define. First, this is two-way. First is you go forward or backward first, yeah, and then you will reverse the direction. Okay. First, you don't know, right? So in that case, you just define all the equation. Okay, until you reach B. After that, you go back. That's how you do. Okay. So first, I need to know from A, what is that? A depends on C and D. Okay, and then now I'm in C and D. In C, I depends on E and F. In D, I depends on F and G. That's how you need to define. One by one, you need to define. Is it clear or not? Okay. If you understand this, you can solve many problems, not just sort the spot, you know. Yeah, the same thing. Now you are in stage 3 now. Yeah. In stage 3, you have 3 nodes, isn't it? E, F, and G. Correct? Okay, tell me. If you are in E, what you will do? There are only 2 choices in E. Huh? To go to H or to go to I. Yeah. So SH and SI. Again, what is the meaning of SH? That's the minimum cost from H to B. Okay, what is the meaning of SI? That's the minimum cost from I to B. Yeah? So in that case, you just add, yeah, from E to H, add with 2. This is the link cost. And then from E to I, this is the link cost is 1. So you got that. Is it clear or not? So you're collecting this equation, yeah, E, F, and G, the same thing. You see here, F, well, this is F. Go to I and J, right? I and J, these are the link costs. And then from G, yeah, go to J or K, isn't it? So that these are the link costs. Up to here, is it clear or not? Am I too fast or too slow? Or just okay? Is it clear? You can do it, right, by hand, okay, in paper, okay? So let's continue that, okay? In stage 3, you have H, I, J, K, right? These are the nodes in stage 3, yeah? H, I, J, K. Again, in H, what you will do, you have only one possibility, isn't it? Which is 3 plus SL. In I, what you will do, you have 2 possibilities, L and M. So these are the possibilities. The same thing in J here, you have M and N. And then in K, there is only one possibility, that is to go to M. So these are the equation that you input. Yeah, you're collecting the equation in stage 4. Up to here, is it clear? Yeah. So these are all the possible minimum. Yeah. And then go back, go to the next stage, which is stage 5. Yeah. In stage 5, you have L, M, N. Okay. In L, the possibility is only one, okay, to go to O with the link cost 5. Yeah. In M, you have 2 possibilities to go to O or to go to P. Yeah, with link cost of 2 and 8. And then in N, you have only one possibility to go to P, isn't it? So this is the link cost. Up to here, clear, yeah? Exactly repeating the same thing, isn't it? Yeah? So, and the last one is stage 6. So now you have in O and P. Aha! Now you get the last point, which is the destination point, isn't it? B is already there. So there is only one possibility, finally. Okay. So to go to B. So what you will do? Now we go to the second part. Okay, you collecting all the recurrent relation already. Okay, now you define the boundary. Okay, and okay, what is this? The minimum cost from B to B? Zero, right? Yes. So that means this is 0 and 0. Easy, yeah? So FB is 0. This is the boundary, isn't it? Okay. So once you get the boundary, what you will do? Reverse all the. Okay, because you know SP, can you get SO and SP? Yes. Oh, now you know, come back again here. If you know SO and SP, can you get SL, SM, SN? Yes. See? And then now you get SL, SL, SN. So can you get SH, SI, SJ, SK? Yes. Come back. Can you see? Everything collapsing. Isn't it? Nice? And then come back. Yeah? So if you know SH, SI, SK, and so on, so you come back to the previous state up to finally come back to A. Is it clear now? That's how you do dynamic programming. Question. If you understand, so think about, yes, just it.
Sir, can you not solve it from the end already?
Yes, you can solve it from the end. So in reality, okay, dynamic programming comes from the end and then come back. Okay, so this is how you do it in the end. So once you have, so this is called backbart computation. Okay, so once you have this SP, so you get 0, and then come back. Yeah, this is already given. So go back to stage 5. Okay, and then go back to stage 4. This is, oh, look at this, yeah, example here so that you will see. So, which of this, yeah? So this is only one, but this is 2, right? So which one that make the minimum? O or P? Okay. The minimum here is 4, this is 9, right? So the minimum is 4, that means you are using O. That is the route that you will use. Okay, you record that. That is the route that you will use as shortest path. Okay, you're not just recording the number here. Okay, but you also record which path. Is it clear or not? So the same thing. Come back here. Okay, at this point you will. This one is only 1. This one only 1. But this one is 2. This is 10. This is 8. So the minimum is 8. So you will use SM here. This one is 6 and this is 7. So you will use 6. So again, you will use SM here. Yeah. So this is the node that you will use, M. Okay. So you record that node because that node is the one that you will use as your shortest path. Okay. Is it clear? The same thing here. So you record which node actually creating the shortest path. Yeah? So 1 plus 8 is 9, and then 2 plus 6 is 8. So the minimum is 8. Which one? J, right? So you record that. Okay. Come back to stage 2, the same thing. So you will record, okay, which one is creating your minimum. Okay. From there, you get back until the stage 1, which is your origin. You get the minimum 13. Okay, the shortest path you just recorded a while ago. So these are the shortest path, yeah, the one in the red box a while ago. So nice. Okay. Now, shortest path can be used for any problem, yeah, not just for path in terms of cost, isn't it? So you want to find a decision, right? Okay. In your life, you want to, oh, this one or that one. Okay. So, and then you try to do a sequential decision, yeah. Then you can use the same thing, yeah. So this is why I need to give you this dynamic programming so that you can do it manually if you want. Okay? Later I will tell you how to use the software, but not TP and the LP. Yeah. But at least you know how to do manually so that you can solve any other problem. Clear, yeah? Computational. Okay? I want you to practice later, yeah? But look at this, yeah? So why TP is important? Yeah, why dynamic programming is important? You compare the number of computation, okay, the number of addition, and the number of comparison. If you do it brute force, yeah, by listing all the possible paths. This is only simple, right? Only 6 states with only 20 nodes. Yeah. So n is the number of states, which is 6. Okay? And then the number of paths is actually, because this is up and down, so divide by 2. Okay? So this is combination. Yeah? This the meaning of combination is this is the factorial. Okay? So if you have n, 6 in this case, the number of paths is only 20. So that's why we can do it using brute force. Yeah? But imagine if you have many. Yeah? So if you have many, these are the number of addition and this is the number of computation comparison. Okay. So if you have 6, you have 20 path. Okay. And then you have 5 addition, 1 comparison. In this case, the number of computation is 119. Okay. Okay. So, but if you have many n states, yeah. So if you use DP, okay, instead of 119, okay, the number of addition and the number of comparison is less. Yeah? So in this case, only 33. Okay, so DP, dynamic programming, reduce the number of computation so much because of the recursion. Okay, so imagine if you have similar like that, but acyclic network, okay, but n is 20 instead of 6. Okay, what will happen? Okay, if you use brute force, okay, you will have okay, so many. Yeah, if you use TP, you only need 420 addition and 100 comparison, very fast. Okay, but if you use brute force, you will have like 3 million, yeah, 3.5 million, and 184,000 comparison. Yeah, so basically, for bigger problem, BP is much more efficient, yeah, than brute force. Okay. So now is the time for you to practice. Yeah, I have 2 example for your very simple network, only 5 nodes, I think. So can you do it on your own? Yeah, the solution is already there, but I want you to do it so that you will practice this. Yeah. So remember, yeah, you specify the node origin destination, okay, and then check destination node, okay, then compute the minimum cost from all incoming arrow, yeah, to that node, okay. So and then you do not make cycle computation, yeah. If cycle infinity, so you just ignore, okay, and then you follow the node in the minimum cost computation until the original. Yeah. Okay. So you keep the list of node that has been included in the equation and then you ignore later. Okay. So this is the problem that you need to solve. Yeah. 2 problem I give you. This is the one that we will use in the traffic assignment slide last time. Yeah. So you have only 5 nodes and how many links? This one is the number of links. Yeah. So this is the node number in yellow, and the orange one is the link number. And the number here represent the cost. Okay. So can you try to solve this manually? And this is the first one. So you go from node 4 to node 1. The second one from node 1 to node 5. Okay, I give you time to practice, yeah? And this is the answer, but please do it so that you will have confidence. Okay? Okay. So you have the slide, so please do it, yeah? And when you finish, you show your computation, and you share your computation. Okay? So I will pause the recording.
Finished completing the node 1 to
Okay.
5.
Okay, so
Let me share my screen. I just used Notepad for.
yeah, it's okay. Yeah.
So yeah, for the first stage, I started from node 5. So
Okay.
that's the minimum of S3 plus 10 and S4 plus 10. Then from there, I computed the S4 and S3 for stage 2. Then for stage 3, S2 and S1. S1 is 0 since it's the road.
Mhm.
So then computed from here. So since I already have S1, this is what I used, 20. Then I proceeded to S3. But
Okay.
I got S1 and I got S2. So I can compute that. And for S4, I also got S2. So I computed that as well. Then for S5, I got this values. I already have S3 and S4. And
Yes.
from there, I identified that the shortest path would be from 5 to 3 to 1.
Okay, good. So there is from in node 4, okay, in node 4, there is possibility to come back to node 5, right? But that path is not used because it will create cycle. Okay, so you need to identify the one that will create cycle you should not use. Right? That one is probably the difficult part. Yeah, thank you, Lian. Very good. Anyone else? How about the others? Okay, one more. How about the from node 4 to node 1? So you can continue Lian, node 4 to node 1. I think the same, yeah. But the challenge is in node 3 in this case. So the one that how you trace that this is come back to create a cycle. That means from say for example from S1 go to S2, right? And then from S2 you go to what is that? 1, 3, and 5. Okay, so but one is already there, then you don't use any. So you have what is called taboo list. Taboo means don't do. So you create that the one that you already have. So as a taboo list. You don't put that anymore. So the same thing in node 3. Yeah. So 3 depends on 1 and 2, but 1 and 2 is already there, so become a double list. And then you continue to the one that you did not compute, which is node 5. Yeah. So, and then the last one is the node 4, which is the origin. Maybe I should here. So in node 1, it depends on node 2, right? And then node 2 now depends on this one is reverse, so you put it. Okay. So you need to get from 5, 3, and 1. Right? But 1 is already there, so you don't need to use anymore. Okay. So you have only used 5 and 3, because 1 is double. Okay. The same thing now, 3 depends on 1 and 2. Yeah, right? So, but 1 and 2 is already there. Okay. So we put it into double list. So you put it into infinity. So we don't need it. Otherwise, it's a clear cycle also. So the difficulty here is when your network is complex, so you need to maintain so that there is no cycle. And same thing here, 5 depends on 3, and this one 4 problem, but node 4 is already origin. In that case, now you can just come back, okay, to get this one. So is it clear or not after you practice and getting the idea of this dynamic programming? Okay. Anyone still want to share? Now, using dynamic programming, you need to develop the formula one by one, okay, manually. Okay. Now, I want to go using solver. Yes, Joshua, you want to say something?
Yes, Prof. Just want to ask if because there's two methods, right? The one going forward or the one going backward. Um, so the one I did was going forward from
Hmm.
from S4 to S1. Which one is more efficient in
Uh,
producing in solving and also in presenting?
yes. So the first example a while ago, that very long, this one, I go from beginning until the end, right? And then in this example, I'm using the other way around, isn't it? I go from the end, okay, from node 1 to node 4, from the destination to origin. So this is actually more efficient. Yeah. So it's not from origin to destination, but from destination to origin. That is the one that usually use more efficient. Yeah. Okay. Yeah, it's good question. Yeah. Yes, Justin.
With this kind of backward method, sir, uh, you still need the stages.
Yeah, exactly the same. So, but in
See,
here,
I got confused earlier when I was trying the example. I was
okay.
the
Because I
example.
reverse, right? The formula I reverse. This is actually still the stages, but because the network is now no longer simple, okay? So the stages is no longer vertical. That's exactly the question that you asked a while ago, right? So
Yes, sir.
the way you do is actually look at this. This is going example in this slide, yeah, going from node 4 to node 1. So now you go destination is node 1, right? So here, so what is the state before node 1? Okay, so you look at the arrow that going to this node. So here there is only one arrow going in, isn't it? So in this case, this is the previous stage. Yeah, 2. Okay, so a while ago you are using outlink. So in here you are using inlink because we reverse the process from destination to origin. Yeah? In the beginning, you use the other way around. So the same thing, the result will be the same, right? If you use from origin to destination or destination to origin, exactly the same. Okay, but this is another way. Yeah, the one that I show here. Yeah. That's exactly what Joshua was asking. Which one is more efficient? Yeah. So the result is the same. Okay. It's just which one first, right? But computationally, this is the one that usually we use, yeah, because this is more efficient. So the states depends on the previous in here because you go from destination to the origin. But if you go from origin to destination, the state will be in the outlink. Yeah? In here is inlink. That's the only difference. I hope this is clear. Yeah. Your question means you get a very good understanding already. Okay. Good. So now let's go another general way. Yeah, you already learned this, or maybe you learned this in other courses before. Linear programming. Yeah. So let's solve linear programming. Let's solve shortest path using linear programming. Okay, using Excel solver or solver in Google spreadsheet. That's okay. Okay, so we are solving shortest path using linear programming. Actually, I should talk about transshipment, but maybe next time. Yeah? So this is a special technique of transshipment problem to ship one unit of flow from the source, yeah, to the sink. And the source represents the supply, the sink represents the demand. Yeah? This is just to connect a transshipment problem with shortest path. Yeah? So the technique, simple. Okay, first you define the flow. Okay, so how you will define? You define the flow as X here. Okay, just definition only, so you just keep name. Is that okay? So you keep name X1 from I to J. Yeah, from node. This is a link flow from I to J. This is what you want to know, isn't it? Okay. And then this is the given, yeah, the link cost. So let's put it as CIJ. Is that okay? So when you want to do linear programming, okay, you need to define the objective function and the constraint. Okay. So what are the objective function? The objective function in here is the minimum sum of the link flow multiplied by the link cost. Okay, that means Xij multiplied by Cij. Yeah. So, and then what you will do, you create a constraint. Okay, this is the one that create the real solution. Yeah. So first, you put the outlink as negative, yeah, the inlink as positive. This is just agreement so that you will get the result, yeah, correctly. And then you put the node origin has flow -1, and then the node destination has flow +1. Okay, and then all the node in between have 0 flow. And then the flow must be all binary. These are the way to do, yeah, using linear programming. So the difficult part to use linear programming is actually to create this. So I already give you, so in that case, no more problem. Yeah, all you need to do is to create this. Yeah, what is the objective function and the constraint? Yeah, so I give you already. So what do you want to do? I put it in formula so that you get idea. Yeah, you want to find the flow. Yeah, in the network. Okay, and then the objective function is you want to minimize the flow multiplied by the cost. Okay, that means the cost is given. And then what you will do, okay, here, yeah, you set the outlink negative, inlink positive, and then you put the node origin -1, node destination +1. Yeah. So here, if it is node origin, you put -1. If it is negative destination, you put positive. Okay, all others you put 0, and then the flow must be binary. Okay. So can you read this formulation? Okay. So once you know the formulation, all you need to do is to input this into Excel. Okay. So let's go back to the same, exactly the same problem that you have. Yeah. So I have from node 4 to node 1, you already did using dynamic programming. Okay. Okay. Now we will use Excel. Okay. So the solution is here a while ago, right? So now we will use Excel. So I copy again the network here so that you will see. Okay. So what you will do, you want to find the flow. This is the flow, right? X is the flow multiplied by the cost. The cost is already given in this link. Yeah. So for example, 1, 3, and the cost is 25. So in that case, 25 times the X. X is the flow of 1, 3. Okay. And then 1, 2. Its link here is the flow. Yeah. So its link 1, 2 here. Okay, what is the cost? 20. So you input that 20. The same, all the links here you input the cost and then the name of the flow. Okay, and then what is the formula? Based on each node, because you have only 5 nodes, so you put it one by one. Yeah. So remember here a while ago I said, okay, if it is out link, you put negative. If it is in link, you put positive. Yeah. And then if the node origin, you put negative flow. And if destination, you put plus. And then node, all other nodes are 0. Okay, this is the one that you input here. So what you will do here, node 1. Okay, node 1 is +1. Why? Remember, +1, what is the +1 means? Okay. +1 means this is destination. Okay. -1 means this is origin. So you will easily check that. Yeah. Okay. So you have only one +1 and yeah, this one -1. So these are the origin and destination. All the others are 0. How about this left-hand side? The left-hand side, you will see, yeah. So node 1, can you see? Out link, so going out to go to 3, right? So negative. And then going out again here from 1 to 2, so negative again. And then going from 2 to 1, this one, 2 to 1 is positive because in link. Going in, I receive positive, yeah. Going out, I need to give so negative, yeah. Is that clear or not? Okay, so you do this one by one, okay, for each node, yeah. So can you see node 2 again? So that you will see the node 2 have how many links here? 1, 2, 3, 4, 5, 6. So okay, so we will put one by one, going in from 1 to 2, right? Positive, yeah. Going out from 2 to 1, negative. Can you see that? Okay, and then to the 3, going in and going out again. Yeah. So 3, 2, positive, and then 2, 3 is negative. And then going in from 5, isn't it? So 5, 2 is positive, and then going out to 4. So 2, 4 is negative. Is it clear or not now? Same thing in node 3, yeah? So how many? 1, 2, 3, 4. So you see, if all the link that going in positive, the link that going out negative. Yeah, this is how you define. Yeah. So and then all these are all the flow are binary, yeah, either 0 or 1. Okay. Up to here, is it clear or not? Okay, good. If it is clear, so this is how you will put into Excel. Yeah, this is the one that you input into Excel, yeah. Okay. Now, so in Excel, what you will do? Okay, initially you just name it, yeah. So you give the name, you just type the name. X12, X13, and so all the links. Okay, and then you keep name here, yeah. You highlight this and then keep name, yeah, based on this one, yeah. So the name from the left side. And then the cost you input, right? This is the one that given. Yeah. Okay. And then, this is the tricky part. Okay. The tricky part is to input the left-hand side. Okay. The left-hand side here, how do you input? The input is based on this formula in the left-hand side here. Can you see that? Okay, so that's why you need to put this formula first in order to create this Excel. For example, yeah, node 2 here, you will see here, I give the formula, yeah, x12 minus x21 and so on, which is exactly the same as this one, yeah. Can you see? Okay. And then once you have this, all you need to do is just input the right-hand side. You just type this one, yeah. This is which one is destination, which one is origin, and the others are 0, right? And then you just multiply the flow, multiply by the cost, and then you sum. So this is the sum product. You get Z. Okay. So you open the solver. Okay, you minimize the Z subject to constraint, the left-hand side equal to the right-hand side. And then all the Xij are binary. This one is the way to do, yeah. So you minimize the Z, yeah, this one, J14, yeah, right? And then you minimize, and then changing file, the yellow part, yeah, this is the flow. Yeah, C3 to C12 is this one, yeah, C3 to C12. This is the flow. Okay, and then the constraint, okay, the flow C3 to C12 must be binary. So you add that, and then these are the constraint for each node. Okay, so the left-hand side must be equal to the right-hand side. Okay, and then this is should be non-negative and then solve. Okay, when you solve, you will get there the result. Yeah. Okay, the flow will be filled with 0 or 1. Okay, this represent the shortest path. Yeah, and this is the shortest path. Okay. Of course, after that you need to check. Yeah. From where to where? From 4, 4, 5. Okay. And then 5, 2, and then 1. You just trace based on subscript, you will know the path. Yeah, if you know the one that have one, that's the shortest path. Yeah. Is it clear or not? Okay, you practice again, yeah, so that you will know. Then you can solve two problems, yeah, from what is that a while ago? From 4 to 1, and then from 5 to what? 1 to 5. Okay, so easy. This is only changing the positive one and negative one in the right hand side. Yeah. Okay. So the most difficult part is actually to create this formula in the left hand side. Yeah, with this based on the network. This one. Yeah. Okay. Okay, try. Yeah, if you don't have Excel, you have Google spreadsheet, the same, exactly the same. Yeah. Don't forget to keep name, otherwise you will get confused. Okay. If you are done, you can share. Okay. So Excel have easy way to create name. So all you need to do is type this, okay, and then put like this. You highlight, okay, and then I think you go to formula. Oh, there, and then you create from selection like this, okay, and then you check left column, then click OK. Yeah. Then the result will be, see here, the name is already there in the name box. Yeah. So that you don't need to type one by one. Mhm. initial flow is up to you. You can put all 0 or all 1. That's okay. Yeah. Yeah, the result will be exactly the same like your dynamic programming result, right? There's no different here, but this is you practice using Excel. That means next time if you have any other problems, you can also use the same. So usually I put all 0. This for the problem 4 to 1. Yeah, so 4 is -1 and 1 is the destination, so +1. And then if you look at the formula, is already all here. You need to include all the formula based on this network. Yeah? The left-hand side is basically the inflow and outflow of this network. Okay. So once you have this, all Z is just the sum product of these two. And these are all numbers. So the same thing with the cost, all numbers. Just type. Okay. Once you finish, so you go to data and solver. Okay. So minimize the Z here. Right? And then changing the variables is the flow. Okay. And subject to constraint. The flow must be binary, and then this and the H and I, this is the left-hand side, must be equal to the right-hand side. Okay. And when you solve it, so you get the solution, there you get the answer. Yeah. So to go to different origin destination, you just copy this. Okay, you copy this sheet, okay, and then you rename. Okay, I have 1.5. So all you need to do is you don't need to do anything else except changing this part on the right-hand side only. Yeah, because now the origin destination changed, isn't it? So that's it. And then you run again. So I can copy all 0 or all 1. Okay. And then again solver. Okay. Exact the same solver, so you don't need to change anything. Now all you need to do is only change the origin and destination here. -1 and +1. Okay. And there. Oops. Cannot solve. Okay, because if you cannot solve like this, this is because the initial value is problematic if you put 0. Okay. So in that case, you start with 1. Okay. So start with all 1. Okay. So if you start with all 1, you get 160. And you do exactly the same solver and run, there you get the solution. Yeah, initial value matters because solver, in this case, you see here, this is using this algorithm. Yeah, you can use simplex, you can use evolutionary mean genetic algorithm. If you use the GRC nonlinear, that means you are using Newton method. Okay. So Newton method depends on the initial condition. Yeah. Actually, all the search depends on the initial condition. Yeah. There. So right. Okay. I hope you can do it. And once you do this, we can move on. I'll wait until you share, at least one of you. Yes, please.
Just questions, sir.
Okay.
For the left-hand side, how did you binarize the flow?
Oh, I don't binarize the left-hand side, but the left-hand side is just the flow.
Just the
Okay.
flow.
Yes. So let me see. So the left-hand side is actually this formula. Can you see?
Okay, so that's there's no cost in that, just the
Yes. So
okay.
if your flow is 1, for example, initially you said 1, that means here is -1, -1, +1. How much? 1, supposed to be, yeah. So this one is your flow is 1, so positive, negative, no more, positive, negative, no more, and then positive, negative. So this one becomes 0, right? If your flow is 1. If your flow is 0, all 0, then. So if your flow is 1, for example, here, 1 + 1 - 1, so become 1. Yeah. Here becomes 0. And this one becomes 0. So initial value, okay, if you put initial value, then the flow will become exactly like your initial value for the left-hand side. So this is the left-hand side. The right-hand side is there. Okay, let me show you the example that you will see. Okay, so example here, right? So I put 1 so that you will see. Then I copy. Okay, see? The left-hand side, this one is negative, negative, positive. So 2 negative, 1 positive. So -1. Right. So here, positive, negative, positive, negative, positive, negative. So this is always 0. Okay. Here, this is 1 positive, 1 positive, 1 negative. So this one is 1 if you put 1. So this is only formula. What is the you need to understand the meaning of this formula, not just input. Yeah, inputting is okay, but you need to understand what is the meaning of this formula. X24, this one, right? X54, okay, and then negative X 4, 5. What is the meaning? Look at this node. What is this node for? There. Look at this diagrams of the network. Yeah. In node 4, look at the link. You have two links going in, right? So 2, 4, and 5, 4. And then you have one link going out with this 4, 5. See, this is exactly represent the inflow and outflow. Yeah. Inflow is positive, outflow is negative. That's it. So this is left-hand side here represent the connectivity in your network. Otherwise, how can the program knows about your network, right? So you need to input that. How you input that? You put the in and out. And then the linear programming understood that you are talking about this network, not the other network. Clear? I want you to try this because this once you understand the left-hand side type and then you run and it worked for you, then I hope you start to understand the meaning. In the big picture, you're defining the flow, you don't know, so you just define whatever it is. It's in one. Okay? And you give the cost, okay, and you multiply the cost and the flow, this under some product, right? And then you give the connection, the connectivity of your network. And then you decide which one is positive and negative represent the origin and destination. Okay. That's it. So once you have that, okay, all you need to do is just solve this. Yeah? This is the beauty of linear programming, right? Because all you need to do is define the constraint and the objective function. Yeah. At first, it seems like complicated formula, okay, but this is actually very helpful because using this, you will define everything. Okay.
Prof, yeah, just a clarification.
Yes, please.
Sir, yung the right-hand side is the constraint.
Yeah, the constraint
And then-
consists of left-hand side and right-hand side here. The
Okay.
equal, can you see this? Equal.
Mhm.
So the left-hand side of this equal
Okay.
is the LHS, yeah. The right-hand side of this equal is plus
Yeah, that's
0, 0, minus 1, 0. And the formula here is just some product, isn't it? The minimum Z is just some product of the flow and the cost. So even in Excel, even simpler than this formula. Dennis, is it okay for you? This one? You understand?
Yes, sir.
Okay.
I tried here.
Okay. Yeah, if you have any problem with my lesson, so you can just direct message to me. Okay, I give you my numbers and so on. So anytime, okay, within 24 hours, I will answer you. Tell me, what did you learn using this feedback?
Prof, I think I got it.
Oh, feedback.
Uh, Can I share?
It's short, please.
Okay. This one. So here, this is the name of the links. And then I was confused first with this one because I had it all zero. Then
Right.
this one yes. So I did solver and I only had this constraint.
Walang yang control mo. You need to put it as binary. You add this constraint represent the left hand side equal to right hand side, right?
Yes.
You need to add binary. Add that the flow must be binary. So you highlight the flow and then you put pin. Yes.
Okay.
Okay, so you
And
saw
then
that one is the flow. Again.
changing the variables, the C3 to
Yes, the one that in yellow. Yes.
then these are the constraints H 3 to H7 is equal to I 3 to I7 and then minimize the Z
Z.
which is D14.
Yes.
So
So if you solve, maybe there is some mistake in your left hand side. So,
I deleted my formula a while
okay.
ago.
Yes. So
A while
if
ago
you
it worked.
right formula, it will not work.
Let's
So you can point if you want. You can actually you go there and then you point to the actual flow plus or minus. So equal. So you just put equal, right? And then what is the formula? Node 1, yeah. Node 1 is minus x13. Okay, and then minus again with x12. No, not one, still not one. Not one have three things. So yes, and then positive x21 is 5 is positive. No, C5 is positive. The other one is negative. C3 is negative, isn't it? Yeah, okay. So then again, node 2, you check the formula, then have median. So positive x12 minus x21 and so on. That formula very helpful.
yeah. I accidentally deleted it a while ago. Wait. I'll just do this quickly.
Yeah.
Equals
Positive x12 negative x21 positive 32 and then
negative 1
yes, positive 32
positive 3 2
negative 23
positive
negative 23 and then positive 5 to okay, so not 3, you are in not 3 already.
no, yeah, no 3.
And so positive 1 3 and 2 3 and then negative 3 2 and 3 5. Okay, node 4, positive 2, 2, 4, and 5, 4. And then negative 4, 5. And then node 5, positive 3, 5, and 4, 5. And then negative 5, 2, and 5, 4. Okay, so and then you solve. If this is correct, you're supposed to get exact the same. You solve for
Solver. So
yeah, just run. Oh, why 40? It should be 45, I guess. So maybe that there is some constraint that is not correct yet. Oh yeah, there is
Or-
probably with related to 5.2 supposed to which constraint have related to 5.2? Maybe node 5 or node 2. Can you check the constraint in node 2 and node 5?
X35 is C9 or negative 5.2, negative 5.4.
And node 2 maybe.
2 is positive
Positive 1,
1, 2,
negative 2, 1, positive 3, 2, negative 2, 3. I think kulang yung positive 5, 2, and then negative 2, 4.
and
Is that correct already?
Two, 3, positive 5, 2, then next,
Negative 2, 4.
maybe, I think I need to name this.
Yes. Naming is easy. You just highlight the two B and C columns. Yes. And then I think formula. Then
Name manager.
copy from create from selection. Then there and then just click OK. There you have it. So you click the C3, for example. It will give name. See? Yeah. So yeah, you need to do it again.
Okay, sorry.
Yeah, no problem. But
I
at
tried
least
it.
you get the idea, right? So
Yeah.
how about the others? I hope this is clear enough. Yes, Justin, you want to say? You want to?
I actually am having trouble with the solvers, sir.
Oh, okay. Tell me.
Can I still share just
No.
to get your insights, sir?
Yes, yes. I don't share myself. Okay, you share.
Uh, is it visible now, sir? Yeah.
Yes.
So
Okay, because you did not set binary.
I have it, sir.
Binary, and
Yes,
then
I'm having an error when I add. It says here this problem this error box.
the cell is not valid. Oh, some of your Excel is not valid. Which one?
Not really
Okay,
sure,
okay,
sir.
let's do it by one by one. Okay, close this, no problem, cancel. Let's do it by one by one. Cancel first. Oh, no.
I
Share,
okay.
share.
Sorry,
Let
sorry.
me help you so that this is recorded. The others can also continue. Okay, say put all the flow one, then copy down. Okay, there 160. That's correct. Okay, let's check the this one. Let me check here. If you put 1, you're supposed to get -1001. Is that no, this is not correct. So your formula is incorrect.
Oh,
Okay, so you need to correct the formula first. Can you?
I'll go back to the.
You can just copy the slide, the
Yeah.
LP formulation, and then put it here. Okay, there. Okay, let me help. Okay, so let's go to note 1. Can we see note 1 is -13 minus correct and then positive. Okay, correct. Next. Note 2. Positive, negative, positive, 3, 2, negative, 2, 3, positive, 5, 2, and like, oh, why have
Oh,
X
okay. There's
before?
wait. I think I see it now, sir. I think all my
There,
20.
also the same.
Okay.
You have
Okay.
also the
I forgot to tab.
Okay, that one is 3, 5.
Oh, wait.
Okay, now you run. Yes, you got, oh,
But it's still 40.
540. Something is still wrong. Maybe.
I'm verifying the
Oh,
formula above here, sir.
check
The Z formula I'm verifying.
the C should be correct one for.
It's still,
Oh, no need this one. Don't. You just sum product. There's only sum product. Maybe
okay. I
that's the problem. So sum product.
read
Yes, on the
this.
flow. No.
Oh,
The left, the flow, comma,
and comma the
yeah, and
cost.
the cost.
There's a much shorter.
Yeah, that's short.
Still 45.
Should be 45. Why
Let me
52 is not there? So must be something wrong. Either the formula or maybe the left hand side is the most probable cause of the problem.
okay,
Uh,
sir. I'll keep
Note 2, can you check note 2? Note 2 supposed to have 1, 2, 3, 4, 5, 6.
Oh, 1, 2, 2, 1, 3, 2, 2,
5,
3,
2. That's
5,
correct.
2, 2, 4.
Correct. Note 3. Can you check? So that you need to do it that.
Yes, sir. It's okay. 13, 23, 32, 35,
Oh, okay. And then note 4.
24,
24, 5, 4.
4, 4, 5,
That's correct. And then note 5, 3, 5,
35,
positive,
5,
negative, negative. That
just
should be
4.
correct. And I know. The right hand side should be positive there.
Okay.
That one.
Then
And then
next.
that was negative. Yes.
Okay, sir. Then
Yes. Okay. Now
I'll
you
run.
got.
Wait. I Yay.
Yes. Okay. Just different origin destination. That's
Okay,
why.
okay. My bad, sir.
Yes. Very good. I hope, but you understand the big picture, right?
Yes, sir.
Right. So the big picture is actually in the left-hand side. That the detail formula, that is the one that I know it's complicated, but that's how you input your network inside.
Okay.
Okay.
I'll
Super.
stop.
Clear? How about the others? Is it clear? Lian, clear? John, Kenneth, Ken? Super. So once you have this, okay, so basically, remember, yeah, the node in the network represent your decision. Yeah. Uh, if if UP asked me to teach next semester in 258, yeah, usually I give decision 3 and so on. So that's more enhanced than this one. Yeah. So the node in here represent decision node. Yeah. For example, if you want to buy or to replace the equipment, for example. So it's exactly the same. So if you buy, what is the cost? If you replace, what is the cost? So you can start to see, you can generalize this problem, yeah, not just shortest path, okay, because this cost represent anything, yeah. Okay, so I give you, can I give you assignment of this one? Yeah, so I give you the problems and you can start to practice, yeah. And anyway, you can use Dijkstra or dynamic programming, or you can use linear programming. That's what you challenge yourself. Okay. Okay. Next, let's go back to traffic assignment. Okay, the one that we missed last week. Yeah. Okay. Traffic assignment. Okay. Can you see the screen? So in traffic assignment, okay, your whole point is now you already have, this is the fourth step model. Okay, so this is the last, and that means you already have the trip gen, that's to get from the population, land use, and socioeconomic, you get the generate traffic for each zone. Okay? And then trip distribution using gravity model, for example, you already get the OD, origin destination. Okay, and then in mode choice, based on your factors, so you already get which mode. Okay, so here you assign that, you put everything into PCU values, okay, and then you assign that into flow in the network. Yeah, so the main point is actually you use shortest path a while ago. Okay, now come back. Okay, now you already get the origin destination of that flow. Okay, now you just assign, you know, the flow, the OT flow. That's from the mode choice or from the distribution. Yeah. So this is given from the previous steps. Okay, but the real one is actually very big, right? The OD table. Okay, and then from there, now you get the shortest path. From the shortest path, all you need to do is to assign that value of the flow. Okay, so then you will get the link flow at the bottom of this assignment table. Okay, yeah. So if you don't want to get the shortest path, you can also have all possible paths. Yeah, this is the multi-path, meaning you find all possible path from origin to destination. Okay, and you get all the costs. Okay, and again from that cost you assign probability. Yeah, so the probability is just based on simple. If you know the cost and you know the sum of this cost, so you put exponential. Okay, so then you will get exact probability. Okay, and then from that probability, okay, you multiply by the volume. It is the total is 2000 here. So 62 multiplied by 2000, you get 1, 2, 3, 4, and so on. Again, if you already know the volume for each route, then you put that into the assignment table. Yeah, this is how you do traffic assignment. Okay, so now once you know the flow, okay, this is only one time loading, isn't it? But in reality, we don't do this. Yeah, this is very old way to do. Yeah, in reality, what we do is instead of putting this 1, 2, 3, 4, something like this, So you divide this into very small number. For example, you divide by 10, okay, or you divide by 100. Okay, that means you have what is called incremental loading. Yeah, so you divide very small, and then, for example, you divide by 10. So instead of 1, 2, 3, 4, okay, you become 123.4. Okay, that 123.4 is the one that you load, yeah, into this route. Yeah, so this one, right? 135. Okay, so when you load this, okay, and then what you do is you calculate the travel time. Yeah, after you put the flow, the one that you put here. Okay, so you know the capacity, and you know. Okay. So then you can get the travel time, isn't it? Okay. So because you know the flow and capacity, maximum speed, and the distance, so you get the travel time. So once you get the travel time, okay, now this travel time become the new cost for the second load. Okay, and then you input again the same. You calculate again the shortest path, like a while ago. Yeah, you calculate using dynamic programming or LP or Destra. Okay, and then you assign again the flow, all or nothing, and then you get the travel time again. Okay, so that updated travel time is the one that you put into the cost. Is that clear? So that incremental rating is the one that we do in the actual traffic assignment. Yeah. So there. So you input one by one, okay, using this incremental rating. Yeah. So you get new load, and then you get the new volume, and then you add little by little. Okay. In order to make, okay, the travel cost is all equal eventually. So this is the condition of equilibrium, yeah, for each route. For each route, the travel time must be the same. Okay, this condition of equilibrium is called Nash equilibrium. Yeah, this one. Okay, this is also called wardrobe principle 1. Okay, or sometimes call it user equilibrium. Okay, this is how you behave in real. Nash equilibrium is something that you will behave because, yeah, you assume everyone will not be able to switch course if they use this path. Okay, and then this is based on perfect information. That means all the travel time is known to all the user. Okay. And everyone is selfish. Then they will do this. Okay, that's why you get congestion. And then how if not everyone is selfish? So as a planner, you want to create, you compute, okay, to get new equilibrium. Yeah, with this now instead of everyone is selfish equal, now you change the objective function, okay, so that the average cost, the average total cost is minimized. So in this case, you will have the second principle, which is called social equilibrium or system optimal. Okay, so this is planner point of view. Okay. So using point of view, some will be some trip will be higher, some trip will be lower, but the average will be minimum for the whole system. Okay. Now, if you will not get the same result. Okay. In fact, the Nash equilibrium or the first user selfish equilibrium will always get higher costs. Yeah. So division between this first or principle or water principle and the social equilibrium is called price of energy. Yeah, usually always bigger than one. Okay, that the cost of congestion. Okay, so that is the one that we discuss. Okay, about what is the problem with congestion. It's not ideal. Okay, behavior of people because they are selfish, they are not ideal. So in that case, it's your job as a planner to improve the situation toward the ideal condition. Yeah, which is the social equilibrium. Okay, so you reduce the price of energy. Try to create so that the price of energy is reduced. So algorithmic in the algorithm, okay, what you do is having small number like this, right? So FL is a small number, okay, and then you iteratively input, yeah, so that hoping you get the NAS equilibrium, equal travel time. But in reality, sometimes you cannot get. Okay, so getting that equilibrium is difficult. So there are many methods, okay, to approach that, yeah, equilibrium. So one way is called MSA, method of successive average. So they use new parameter here, V here. Okay, the V depends on the number of iteration. Okay, so N here is iteration number. Okay, so that means if the initial value N is 1, so then V is 1. So the 1 minus 1 is 0, so this one is nothing. And then N2, this is half. Okay, so you give half between the old and the new one. If you understand this formula is called convex combination. Okay, what is the meaning? This is, okay, the new value. This is the old value, right? So this represent the short-term memory. This represent the long-term memory, the system. Okay. If imagine I don't give you the number of 1 over n here. Okay. What happen if I put this one is 1? That means this is 0, isn't it? Yeah, if V is 1, this means the new value depends only on the new flow. Okay. But if the V is 0, that means the old value will be prevail. Okay. So by putting the iteration V is changing over time, dynamically change, hoping we will get converts to equilibrium. Yeah, this is the example of computation. I'm using this formula, yeah, in Excel. I try. Okay, so there's another algorithm called Frank-Wolf, yeah, which is similar to MSA. Okay, but they use different fee here. They use mathematical programming, like linear programming, to compute this fee here. And this is guaranteed to speed up the conversion. Okay. So another method is to use stochastic method. So you use random number and you assign the same thing. Yeah. But using this, because you use random number, then become very, very slow to convert. Yeah. So the new traffic assignment method, there are many, many variations, okay, including ideal flow network. Okay. And in MIT, they develop also dynamic traffic assignment. What is this? Okay, now the OD is dynamic. Okay, so they have the sensing device. Okay, and then this OD is now changing. Then you load this based on dynamic traffic assignment. So that means exactly the same assignment as before, but the OT changed. Because of the OT change, there is also queuing inside. So this become much more complicated than this. Yeah? So all the software that you have, whether it is commercial or non-commercial, is basically about traffic assignment. Okay, so variation of this traffic assignment. So FN is free, so you can use. Of course, not perfect. So I hope you can also help to improve if you want. Okay. Now, for next week, we can also discuss about traffic signal. Yeah. So can you go to the model? I have link there on the slide. And I also have the traffic signal design. Can you see my? Okay, this is based on IFN. Okay, so please try this first. Okay, at home before we have class next week. Okay, so this is just to draw. The intersection is very simple. Okay, so you can just put the compass and then redraw, so you can get this intersection. And then this is the design. So how many lanes that you want? Okay, for example, I put 3 lanes here, 5 lanes there, maybe 0 lane there, okay, and so on. Okay, and then this one is the rule that you can set. Okay, so in the Philippines is right hand side, right? So driving is right hand side. So then you change the rule. Okay, so depending on the input, okay, for example, I have 4, and this is R mean right, S means straight, L mean left. Okay, so see this, the drawing is there. Okay, so you can set that. Okay, this is the saturation flow, this is the congestion level. Okay, and then this is just a drawing of the direction that you set here in the design. And then this is the computation of the flow based on FN or maximum entropy. Okay, and this is the signal timing design. Yeah, there. So you can input your own for your project. You can input your own there. If not, this is if you based on maximum entropy. This is already computed there. Okay, and I have many algorithm that you I put here. Here, I think I have 1, 2, 3, 4, 5, 6, 7. Here I have 7 algorithm that you can select. Okay, so and you can also check whether this is merging allow or differencing allow or not. Okay, so you can optimize the phase. There, you will get the phase. Okay, and how many green time and so on. And these are the phase diagrams. Okay, and you see the color, phase diagram, and this is the signal timing. These are the results, right? Okay, so and this is the actual performance metrics. Okay, your challenge is, of course, when this is very poor, so you need to change, yeah, the design, isn't it? So whether you use pedestrian or not, you can also put there. So pedestrian crossing, you can input. Okay, and this is like commercial software, so you can have also find the best plan. Okay, it will compute, and you get the best plan. Okay, so best algorithm, best cycle time, and the full log is here. So this is very useful for research if you want. Okay, so you can also change. For example, if you don't want this, so you say if you change this, it will change. Yeah. If you change all the result will be changed based on all the input that you want. Automatically. You can also have a platoon constraint so that the intersection will not block the next intersection, because in the city usually very short distance, right? The blocks. Okay. Try this. Yeah, this is similar to commercial professional, but it's very expensive. So I just make it for you, so you can just try. I hope this is useful. So the algorithm is just insight to create this either conflict graph or compatibility graph. Yeah. So graph coloring is just conflict graph. Okay, so try this first, and then the help file is there, so you can read the help file. Yeah. So that you can understand this more clearly. Okay, with that, thank you very much for today. Okay, so you can use this for your projects and continue. Any question, any comment? Okay then. So I'll stop sharing and thank you very much for today. So see you next week. Is that correct? Don't forget for the faculty evaluation. So please